Well, you're probably not surprised because I said I was going to do it. Is that I went out and got Scott Walter because, you know, he is the guy we all need to talk to when something happens in the Optimus world. And thank you very much for watching last night's video. That was maybe the number one viewed video ever on my channel. Wow. When we popped that off last night. So one piece of housekeeping. Sorry, Scott, before we start. This is normally the time when I would do my, what we call Monday morning, which is the financial reporting for this coming week, the things that are going to happen in the financial world and with Tesla in the coming week. We are still going to do that video, but it's going to be pretty late. It's probably going to be like 5:30, 6 o'clock California time before that video, maybe even 6:30 before that video goes up. But we will do it as we do every week. That is the number one show actually each week on this channel. So I'm not going to let you down on that one. All right, Scott. Thank you so much for coming on at a brief notice. I know you have been traveling all over the state of Florida, watching launches and going over to see Optimus. What are we calling those again? We're calling them
Opticans.
Opticans because they're really not Optimus.
They're a mannequin. They're an Optimus mannequins. And
yes,
so
I love
Optican.
That. Anyway, so I started off in the green room a minute ago saying that you had, I thought, oddly said this morning in a tweet, in a post on X that you that nothing was surprising about the video.
Yeah. So I guess let's back up a little bit to how much of the video I got to see with very little advance notice. So my weekend plans were, I wouldn't say they were radically altered, but this almost threw a monkey wrench in the whole thing. So first of all, I guess you're going to be kind of lucky here, Randy, because I already had John and Tesla Fix get their talons into me early this morning to get my hot take. Yes. And it wasn't the ideal situation for the audio quality and everything. The background was kind of nice because there was an Optimus behind me. But now you get my warm take. So I've had a chance to actually mull this over and think about it a bit more, listen to other things. So hopefully the audio quality will be a little bit better, and then the discussion of what the content of that video means and the importance of it. So long story short, this weekend, my plan was to go with CERN Basher to the Cape to watch a Starlink launch. And it's like just before the Starlink launch is going up, my phone is blowing up. It's like everyone just starts, it's like, oh, have you seen this video? Have you seen this video? It's like, oh my goodness. It's a good thing we decided to stay in the Orlando area and not drive in the morning, 3 hours to Orlando with rush hour traffic and everything. So I'd actually have a chance to look at it. Right. So, ended up staying up to about 2 o'clock, looking at it about 30 times. And, I looked at it a bunch of times. CERN was looking at it a bunch of times. You're just trying to figure out what's going on here. Look at the nuance. Everything else is rather interesting. And it was and the whole idea of being in Orlando is that we did a presentation for the Tesla Owners Club of Florida at the Florida Mall, where they have an Optican model there. And we had a pretty good turnout because a lot of people were really interested in, okay, how does this thing work, and want to know a bit more. But I wasn't prepared really to talk about this video. I had my preparation. I was like, this is what it's going to do. And it was kind of good timing in a way to be able to see that and to be able to talk to them. But again, I just had this lousy phone with like really lousy earphones, and we were in the Tesla showroom before they opened up. And like, you know what they do before they open up? They vacuum all the cars. They're like, put on the background, all this other noise. And so it's like, oh, okay. They didn't turn out. So hopefully anyone watching will actually be able to hear my voice a bit more clearly.
Right. So do you want to start with an overview of your thoughts, or do you want to put the video up and take a look at the details? I don't. What we do want to go?
We're going to break it down. So it seems to me there are like maybe 3 really major things that are going on here. Was there anything that stuck out to you right away that you would like to comment on, or you'd like me to comment?
And I'm always forgetting the name of it, but this business that we have as humans where we can touch our nose with our eyes closed, there's a name for that.
Proprioception. Proprioception.
Yeah. Okay.
Proprioception.
So that looked like, is that what they're talking about with regard to those some kind of dots on the on the arms there?
Yes. Basically what they're doing is they're doing a calibration so that you dial in the proprioception to be accurate. So you want to make sure that whatever the internal model is that Optimus has matches, like say, the control output model. So when Optimus is moving the joints, because it's said in the tweet, but not actually in here, but the header to the tweet was video in, control out.
Right.
So it's seeing something. It says, now I need to move my arm somewhere. So the neural net is doing something to say that the joint angles must be a certain amount. And joint angles are basically measured in encoder pulses. So that's why they're called encoders. So the first thing to do is make sure that all the optimi are kind of calibrated to the same reference datum or the same zero. Okay, so the thing about it, if you look at my elbow, and I don't know if it's showing up right now, have my elbow out straight. And
Right.
if I bend my elbow, I want to know what that angle is that it's measured.
I
And
see.
so what you do is you put an encoder there at the joint to measure it. And that encoder is basically an electronic version of a protractor. So just think of it that way. It's just able to measure what that angle is. And as you remember, when you were having to measure angles in school and they taught you how to use a protractor, you would have the two lines and you would line up your protractor such that the zero of your protractor was along one of the lines and the other one would tell you what the angle is.
Right.
Now, if you messed up and you put like one of the lines at 15 degrees and the other one is up at 60 degrees, you might declare, oh, look, a 60-degree angle. It's like, no, that's a 45-degree angle because your datum is off. And so when you construct the optimi, it's not clear right away whether the datums are lined up the way you want them to be. It doesn't know what the reference zero is because the encoder count could be in some random position when you put the orders in there. So the first thing you need to do is get that calibration to make sure they're right. The other analogy I've used is think of like a clock face, a watch.
Right.
So if your hands are in the midnight position, but you take the face of your watch and you just kind of like rotate it around. So now it's kind of pointing at 3:30. It's like, well, wait a minute, that time is absolutely off. So the whole idea is that you want to dial that in to be right. So you get the calibration for that. And now they're doing self-calibration. So how do you measure those things? Do you actually go up there with a protractor and start measuring those angles? That's like one way that you could do it, but it's very tedious. And
Sure.
plus, it's really hard to figure out where are the lines that I'm actually measuring that I'm putting my protractor in there. It's kind of hard to see what the angles are. And you can look at it and estimate, it looks like a 90-degree. It looks like, but that's not good enough. We want to get it very, very precise. So what they end up doing is a calibration, which is common in robotics in general. So all robot manufacturers do this. When they build the robots, it goes through a calibration phase. And there can be a lot of error in a robot. So when you manufacture anything, there's always tolerances and stack up errors and everything else. But hopefully you're making all your arm lengths and everything the same length. And there might be something that happens in the assembly that something's off a little bit. But the major source of error in all the robots is what they call the joint encoder zeros. You're way off when you're zeros. You can be like 5, 10, 15 degrees. We're not talking a little bit. The length of a robot arm might be off by like a fraction of a millimeter or something like that. It's really, really small. So they know how to build these things, but the main thing is you got to dial that thing in. You've got to get that reference position. Very, very important in order for that to work. So all the robots at the factory, when they're there, they then go through this measurement thing where they move randomly in space, and they use something very much like what you would use in surveying. They're actually these lasers that are like theodolites that track what's called a cat's eye at the end of the arm, which basically is a mirror that goes around that's picked up by another sensor, and they can measure that to fractions of a millimeter of exactly where the robot is. They look at all the joint angles, and then they fit that to a model to find out what all the parameters are for the robot, to find out where its errors are, the tolerance errors, and that becomes a signature file that allows you to then compensate. So when you say, I want to go to this particular position, it knows exactly what you have to do with the encoder values to get to that position in space. So that's a very common thing. So that means every robot model has this concept of proprioception that we typically call forward kinematics. So in other words, give me the joint angles of your mechanism, and I can do some math, and I'll tell you exactly the XYZ location of the end of the tip of that finger where it's supposed to be. Right. Assuming everything is built right, and we agree on what 45 degrees means, everything. If we disagree, it's going to be off. So you bring that in to make sure the real world model and the ideal model overlap as best as you can get them. So again, proprioception is the idea that you know where you are and you can get there without looking. So if I can close my eyes, I can touch my nose without even looking. And of course, if I open, it's a lot easier. If for some reason I go and it's like, oh, wait a minute, there's something wrong here. Oh, there it is. There might be an error. So there's a possibility of slippage in your encoders, and everything else can happen, especially when you do maintenance. And so what you need is two things. One, to measure the angles, and the other to measure the actual XYZ location of the end of your arm. And there's very expensive setups that you can use for that. But basically, they all are doing the same thing. They're trying to survey some landmark features on your mechanism. And cameras are really, really good at doing that now. Like iPhones and everything else already are able to pick up landmark features. So what we end up seeing here is when it starts to move around, and it's probably doing these specific moves intentionally to kind of figure out what some of the joint angles are. And then we could see what it sees. And when it's looking down there, you'll see there's no dots on there. But if you look at the hands, you're going to see, oh, I can see some creases in here. I can see some points there in the knuckles. I can see some ends over here on the wrist and a few other places that may be a really good landmark features that I can recognize and pick up. So at some point, the system goes like, yeah, I see those. And remember, Optimus has multiple cameras. You know, it's like us. It has stereo vision, but actually a bit more because it has several others. And because it has the stereo vision, it's seeing both those a little bit differently in those two images. And you can match those images up and from it triangulate to figure out what the actual distance is to there. So that's a very, very common thing that will be done to measure it. Now, there's an important step before that. First, you have to calibrate the cameras, because in order for us to figure out what the stereo field of view is, we have to know the exact distance of our eyes, how far they're apart. Okay. And so you're hoping all the Optimi are manufactured the same, but it's possible the camera is like popped in not quite right. So we do the same thing with FSD. Remember when you first get it, you have to calibrate the cameras, you have to drive around a while. Yeah. So there's like this auto way to, so there'll be one way, first you calibrate the cameras. Now that the cameras are actually seeing everything accurately and we know wherever it is, then you go in there and you basically survey where that is, those different landmark features. And you try to oversample, because the more you get, the better it's going to be, because any one individual measurement is going to be a little bit noisy. But when you have a lot of them, the noise basically comes out in the wash. And now you know exactly where it is and you can dial it in. So it might be one of those things that every time they turn off Optimus, it's like when you wake up in the morning, it's like, oh, I'm a bit bleary-eyed and my proprioception is like really bad. You know, I go to yawn and my hand goes like this. Oh, here we go. So it may be that when it wakes up, it goes through this very simple routine to be able to. So this is very fundamental to robotics in general. So that's why I say, no, I'm not surprised, because they're going to have to do it at some point. I was always wondering how they do the calibration. I was glad to see it because, yeah, I knew they could do it. And this, I suspect, is purely heuristic code. I don't think I could be wrong that they may be doing some other things to get the fitting, but typically it's already a solved problem. You know how to do this thing heuristically. I see. Okay. Now, the second thing that came to my mind was only after I heard you this morning on Herbert, and I'm looking at it right now, is all the wiring that still is exposed. Mm-hmm. Yes. You mentioned that on the video this morning. Yes. And so there still seems to be quite a bit. And remember, this is still a prototype. Sure. And we can actually see a lot of the covers are off and everything else. So we really don't know how much of these are needed cables or how many of the cables that are just there for being able to debug the whole process. I got you. So I suspect eventually they're going to go there, and I'm hoping they're able to find some way to route these things. And they probably are, but it's just like, it's low priority at this point. Right. The other thing to remember is that in here is, so it's using the vision and joint position encoders, it can precisely locate its limbs in space. So it knows exactly where they are. And limbs mean legs as well. So somehow it has to look down on its legs. I'm not sure whether it does that from a standing position or whether it sits down or something else, or whether it's balancing on one foot, because it's going to have to get its leg out there in the field of view in order for that to work right. All right. Okay. So that's what we have here, I think, on that. And then we get to the next part after this, which is, now that it knows where it is, it can actually grab the parts because it knows it wants to get it. So it's the vision in, and now whatever the control out is going to match the model correctly. Right. Otherwise, if it was way off, it would probably really miss the target every single time. So now it's able to learn it, and then it'll probably also easier to transfer them from one Optimus to the next. And we could see it's picking up what looks like, I think with these mega blocks or something like that, to move them into different positions. And a very simple step. We saw Google doing something like this about a month or so ago, of showing how they can pick up parts and move them around. Remember, it was like putting apples in the apple bowl and oranges in the orange bowl. And this is sort of a similar thing, is that they probably are telling it, not which just a very simple instruction, put sort of the matching colors in there. And it's interesting, this looks more like yellow to me than green, but it may be more or less like, oh, the blue belongs there, and this is like kind of the best next thing. Or Maybe it's colorblind. I don't know. one of the other. And, it's been noticed it goes down, and when it grasps it, that the other fingers kind of close. Yeah. And it may be that from the standpoint of grasping, it doesn't quite yet know that, well, you only need the 3 fingers that are the others you can kind of leave out. It's probably just closing it just for good measure. And if they kind of go down, it doesn't. But it actually looks very natural, because if you try taking your hand and clenching it, and then say, okay, now just do the thumb and the first 2 fingers and close them and get the other ones out. It's kind of hard to do that. The other fingers, they just want to come. Yeah. Optimus can actually hold those up there because they're independently derived. As you move one, it's not going to force the other finger to move.
Right.
So, they're just saying, oh, just go ahead and clamp it down, because we're maybe not exactly sure the size of the object, but okay. So that's what it's going to do for a grasp.
But also, if it's watching a human, if it's watching a video, this is video in. And
the human is doing that. The human is doing the same thing. Right. The human is not going to have the fingers out there.
Right.
And maybe you don't want it, because now the fingers are exposed. It might get caught on something. So maybe the idea is to get it out there. So it's not like I'm saying, well, it's like, maybe it is, they have to reference to that. And again, when it's closing, it's almost like it's clenching it from the other side to prevent it from slipping out. So in some ways, it's securing that move a little bit better. Now, it seems to not really care where it puts it in there. I don't think there is a specific target. It doesn't seem like it's going to the center. So like, well, when I get over that, it's good enough. I drop it in. There's no precision in it. It's not like I'm supposed to put it in a particular corner or a certain pattern, just drop it in. Right. So it's going ahead and doing that. Grab there again. And again, we see the 2 fingers that kind of close, and the ones that are there for the grasp. And the thumb, of course, is very important. Otherwise, the grip won't work.
I think a lot of people have noted that it seems natural and smooth.
Oh, yes. Yes. So it's very smooth. And also notice the whole body is at play. Now, for some reason, the left arm is sort of off in this case. It's not moving, but the legs and the hip and in the torso are all part of the movement. And that's something that I really like seeing, because it means it's really an integrated system, as opposed to a bunch of individual limbs that just happen to be sharing the same torso. They understand that when this limb moves, there's going to be reaction forces, and it knows how to react to that. And it's probably moving its torso a little bit to perhaps get a slightly better view, because it can't really move its head, but it does have some torso movement. So again, it might be trying to center things and everything else. And it does seem very natural. So again, it's, only using the vision, and it's a pure neural net all the way through. So there's no heuristic code between the vision and the motion. And that's big. So if there hadn't been much progress in Optimus since, April, it's because they were trying to refine this and getting to work. Because remember, it was, I think, in April when they first got the first end-to-end to work. So it's like FSD version 12. They've kind of torn the house down, and now they're having to build it back up again. So it's like, okay, Optimus hasn't been doing it much lately, but we finally get to the stage that now it's going to accelerate really quickly. So this teaching is impressive. It's not clear how they're doing the teaching. There's the tweet makes it sound like maybe the training was using a lot of videos. I suspect there's a bunch of things. One, watching an operator, because they already demonstrated they want to do something like that. So through the eyes of an operator, maybe watching actual videos, and then maybe some teleoperation, things like that. There could be a variety of ways that they could be mixing it up. Even simulation could be part of the whole mix.
Sure.
And now you notice, again, it just sort of dropped it. I don't think in the same place, but it didn't care that it actually dropped it on the other block. It's just like, it's over there. So eventually you might want to show it. Say, wait, when you put it in there, make sure you're not bumping anything else. Leave a little bit of space or something like that. That's probably going to come. Now, of course, you notice what happened there is it tipped over, right? Because of that, because of the way it dropped it. And we're going to see in a second how it kind of corrects something like that. But right now, it's just, all right, now let's pick up the greens and put them over there. So by color automatically. Now, this is the dynamic reality of the world. So we have a human that's going to come over and play cat and mouse with Optimus and basically annoy him as much as he can. So let's watch this, and you'll see that it's hard to tell whether the human was making sure not to touch Optimus, or whether Optimus noticed the hand was coming in there and decided to move out of there. So this is going to be very important to seeing how Optimus interacts with other humans, right? Because you have the 3 laws of robotics. And in the first one is that A robot will cause no harm to a human, bring no
Right.
harm to humans. That's the very first one. And that basically has to be part of its firmware. It's got to be in there to understand that. So if it's doing an operation, it looks like it's going to bump into someone, it needs to kind of stop that. But, at the same time, the human is the one that's being the aggressor here.
Right.
But it to kind of back off, it's not there. And there's some other little things we're going to look to see. So that's like one of the first questions I want to have. Now, here, it's getting ready. I think this is where we get the target. Oh, did it move? Okay, I think what happened is he kind of hid the target. He played like a little bit of peekaboo.
Yeah.
Let's see exactly what was going on there. So it's right here. So suddenly, I think Optimus is going for, I'm not sure exactly what that hand was all about there, what he's trying to do. He's coming around here. I'm not sure if Optimus was going for that one and went for the other one because it was kind of blocked. So now Optimus was clearly going for that blue block. So in the first case, it may have been, I hit it on you. So suddenly it's not there anymore. So it looks like the next best one. In this case, it's like, well, I'm really going to move it because you were going for it and you could see the motion of the Optimus hand was towards it. And now it's somewhere else. And it rapidly picked it up and moved over there. So there was like no hesitation on where to go. Again, I don't know if the human hand kind of stayed around there. It's moving. It's comfortable to be moving around a human hand, but it doesn't want to hit it.
Right.
Okay, that green block. Okay, it was going for the green block there, and then that was sort of bumped in there. And okay, so it was like, let me back that up a little second. So it's going for one of the green blocks right there, and it's like, whoa, wait a minute, I'm going to move it on you. So now it says it's not there. I have to make a decision on which one to pick up. It doesn't matter which one it picks up at this point. So it says, I guess I'll go for that one. Go for the other one. So it's going around and quickly making a decision on which one it's going to be. So even though the target moves, it rapidly goes and gets that. So one of the things I want to find out is how well it behaves around humans in situations like that to make sure it doesn't bump in or make an accident. The other is wondering is that this persistence model, this thing that when children are very small and you do peekaboo, it thinks you've disappeared or you don't exist anymore.
Right.
It doesn't realize you're behind it.
Yeah.
So, whether Optimus understands that when the block gets hidden under the hand, it's really still there, and whether it would just be patient and wait
right
for the human to expose it again. Or in this case, it just says, well, if you're going to play a game like that, I'm just going to go get this one over here because this is my task that I want to do. Fortunately, Optimus probably doesn't have a temper. Otherwise, he might get upset after a while and push the human away and say, stop this, or knock the hand away. And that's actually something I'd want to know whether that's going to happen in the future, because that would be a strict violation of the first law.
Right
there. And whether that's encoded in there and whether they've thought, and I'm sure they have thought about it. I just like to know where it is in the testing that they want to do and whether they kind of sort of. So now here we have the unsorting. It's able to pull everything out, which is rather interesting. The blocks will bump into it. So that's sort of the training in the AI thing that it's able to do the neural net. So there's a lot there. First of all, that there's no heuristics in there. Just this idea, wow, vision in, control out is big. But then the other's like, well, then how did you teach it in the first place? You want to know that a little bit. And it's like, well, little hints, but clearly it's doing decision making and what's going on. So the next is to find out how they are really teaching and whether they're teaching with videos, and how many videos they're going to need for it to be able to do lots and lots of tasks that are complex.
Right.
Now, this one here, I was expecting them to get to state someday, because we know Optimus is going to walk better and better. They already showed what the evolution of walking is going to be in a video a year ago, where, it's first kind of plodding along very poorly, almost squatting down and getting up, and then the hips are coming out. And then it should just be getting better and better as it goes along. And there was a hint in one of the last videos. Remember the egg that didn't break?
Yeah.
The leg that came down to hit the egg, but it never broke the egg. That was of the leg. And that was showing the precise control that they have on the leg and how rapidly they're able to move it around. So that was already a hint of like, oh, okay, there's going to be a little bit of finesse going on here, and some interesting abilities on the walking. And this, you need the whole body to understand what's going on here. So here's a yoga stretch, proving it can balance on one foot, which is already amazing. And the idea that it sort of knows that you have to get the hands out and everything else to create that balance point, to be able to get that movement. And what's interesting is like the whole body kind of gets out there. And right at the end, only the leg moves. The planted leg just has like a little bit of movement there to go forward. And part of it might be to get the center of gravity more over the foot. So you're not balancing on a tip. If you're trying to balance on a tip, that's very, very difficult. But because you have the flat foot, you're basically balancing anywhere along there. And there's a center of pressure on that foot. And so long as that center of pressure is between your toes and your heels, you're not going to lose balance. It won't be maybe, you're kind of losing a little bit of the static margin in there. So that means it'll be very easy to almost blow you over at that point. And you'd like to bring it a bit more in the center to get more stability. So it's more of a rock solid position. So it kind of gets there, but it doesn't mean the rest of the body has to compensate for that little movement that you're seeing on down there.
Yeah.
And, you know, it's just really nice to be able to see that, to see the fluidity of the movement, to see how natural it looks, and the fact that it is able to balance so well. And then this one here is like another balancing maneuver, which I was actually able to kind of perform something like that. But the thing you see is that everything is moving. The hips are moving, you know, the arms, the torso, and everything else. And this position, what I like about this is we've talked about how much movement you need to have in your wrist. And, you know, whether the wrist needs to go back and forth like that, because you barely do this with your wrist, but you do this with your wrist and you roll your wrist that way. And the initial decision in Optimus was to not have this movement in wrist. It's what we call yawing movement.
Right.
And it's in Isaacson's book, there was a discussion and they decided to go with 3. So have the full movement of the wrist. The initial Bumblebee only had 2 movements. It could do this, but it could not do that. So it could roll around and it could do that, but it was missing that other movement.
Right.
Now, the way the wrist is actuated and the way the ankle is actuated is very, very similar. So the ankle actually doesn't have the wrist roll that, you know, underneath the knee. That's not there, but it does have 2 degrees of freedom here. And the most important one, of course, is the one we think of when we're walking, being able to go up on our toes, the flexion of the foot. But this kind of twisting back and forth, what we call kind of like spraining your ankle, because, you know, if you're walking on an uneven surface and suddenly your foot goes off the side, it's like, oh, I sprained my ankle. We have a little bit of movement there, not a whole lot, you know, maybe 15 degrees plus or minus, something like that. But it's not like we have the 90 degrees or more that the foot has as far as being able to spring off on that toe. But it's there and it's very important. And a lot of times you think, well, what's it really needed for? Is it ever needed? It's needed to do this. Because in order to get this balance, look at that leg. The planted leg is not straight up, but the foot is flat on the floor. And in order to be flat on the floor, you need that degree of freedom, not the forward degree of freedom, the side to side degree of freedom. It's very important. And you also need to have maybe these actuators here, which are strong enough to be able to react to get you the balance that you need. You know, even though that's sort of an unused axis, I kind of say it's not really there, and that these actuators are really to be able to make the foot jump almost, to put the power in there. When you're doing something like this, suddenly you are more interested in the power to be able to keep that thing stable. And so you need it. And this is the beauty of this parallel design, is they don't have a wimpy little motor for that axis. They get the full force. These 2 motors combined together have the same force as one of the motors in the thigh up here.
I see.
Or the quadricep. So that's a lot of power that's there on demand when you need it. And then, of course, you see everything else that's going on with the body. The knee, that's pretty good range of motion on that knee. I didn't expect it to be able to come up quite that far. So that is pretty good range of motion. And we can also see even the elbow. I don't think I've ever seen the elbow scrunched in quite that much as well. That is pretty good. So when you see something like this, that means Optimus can probably squat down and pick up something off the floor. I don't think it has to like get down on its knees. It might actually be able to squat down and pick something up like that. It'll be interesting to see it, because there could be some balancing issues there, because you've got a very heavy torso that could be leaning in front. And it also brings up some other things. If you look here at Optimus, first of all, the head has been covered the whole time. And the other Optimus video, it seemed like it was always missing the top of the head. And the reason is because it's through the top of the head that you put the hook for the harnesses to keep it up. But in this one, it's not there. It's almost like, are they running without harnesses? Are they that confident right now? It's like, it doesn't fall over. But I think it does, because you do see what looks to be some sort of knee pads on here. These aren't the normal knee pads you see in Optimus.
Oh.
So I have a feeling it may be falling down a little bit there. I don't see anything else on the elbows. And this kind of also begs a question, is that I don't know if Boston Dynamics did this, because when you watch the Atlas videos, when Atlas falls over, he just flops. he just like, I'm falling, okay, and it doesn't even try to get out of the fall. He just accepts his fate that I'm falling, and it will face plant and do whatever. And that just means the mechanism is going to break because you're falling wherever.
Right.
And I know Optimus is designed, they put a lot of thought into making sure that it could fall down without breaking. But just because it can fall down without breaking doesn't mean you can't take some countermeasures to make sure you're not always landing really hard or landing on something else and breaking it.
Sure.
So, John Gibbs is a climber. I'm not, but when I went to the climbing gym with him, the first thing they did is they wanted to make sure I knew how to fall. So before they would let me in and allow me to climb the wall and get everything else, I said, all right, come over here. We're going to show you. This is how you fall. And it's like, oh, you go to tuck position and you come down. This is what you do so you don't hurt yourself. And so you're trained to do that. Gymnasts are trained to fall. Everyone is sort of trained when they're doing a sport like that. The first thing is, what's the proper way to fall? So I was surprised they didn't program. The first thing I would have programmed in Atlas is, all right, let's make sure Atlas knows how to fall. That when it realizes I'm falling, and you still have the IMU and everything that tells you where you're in there, it should just go into kind of this instinctive position that's like, pull the arms in, fetal position, whatever, tuck yourself and roll. So I wonder if Optimus is able to, so that's like the first question. Have they set it up so that it falls gracefully? And second, I would like to see how Optimus gets up from the floor if it does fall down. So when it's down on the floor, if it's on its back, it's on its side, if it's front, doesn't know how to get up. That would be interesting to be able to see that it has that kind of ability as well. And those are just some kind of thoughts that, aren't in the video that we'd love to see.
Like, does it get up like a human? I mean, again, I think the outsider, the person that is not a roboticist watching this video is going, man, those moves are so human-like. I mean, that particular pose right there is, it just has that quality. So that's kind of interesting. So Elon said,
now there's a good chance that it's being coached. I mean, it's a good chance that they're bringing in like a yoga coach or people who know, it might be they're just people on the team that practice yoga, so they're able to do it. I know there's a lot of people that do martial arts, so they might be looking at some of those things as well. And, you can imagine you bring in like a physiotherapist or others. So there are people that teach other people how to get off the ground. So usually when people get older and they start falling down, they don't know how to get up. And the physiotherapist will sort of teach them, well, these are the tricks. This is how you adjust your weight. This is how you want to move your legs and everything. This is the right way. I mean, even getting out of a chair, sometimes people will realize that, suddenly they don't have the strength to get out of the chair, how they do it. And they will show them, this is what you do to adjust your weight and everything. So you might be doing the same thing, that you actually can have these coaches come in to demonstrate what is going on. And that I would definitely do that. Hire like either a diving coach or a gymnastics coach. And, I'm sure they have a martial arts teacher that understands motion and how it works with the body. I would also love to see Optimus on a trampoline. Now, you're going to have to suit Optimus up, because the problem with Optimus comes down the wrong way on the trampoline, he's going to rip it. Okay. He's got some pointy edges there. So, but the thing is, if you get Optimus a little bit airborne, it's going to be free falling, and see how much it can understand what it's like to fall and what to do to counter that motion, so that it gets this better sense of what's going on with its body. And eventually it would be great to see it in, a much greater kind of free fall kind of situation, whether it can, if you like push it off something, does it like a cat know how to like come around and land on its legs every time? But obviously you're not going to be throwing enough of 10-story buildings to do something like that. But, at shorter distances, it would probably be able to, certainly in a trampoline, that it would be able to understand that, how to come down and get that sense of motion and test it out.
So Elon today posted early this morning, he said there are lots of coming additional changes to the actuators. So I suppose it's probably hard for you to see whether there's literal been changes or, because sometimes they're going to be hidden or whatnot, but is there anything that jumps out at you since the last iteration in terms of the actual build?
I've been trying to look and I can't see anything too closely because there's not enough detail. And you see there's a lot of the harnessing around that sort of hides it.
Yeah.
There's nothing that jumps out. And of course, they've exposed everything a bit more. So we can't quite see that. Now, I don't know if he's talking about some internal or external changes to the actuators.
Yep.
Some of the changes they might be doing when I look back at the AI2 presentation, when they were talking about how they were picking the different actuators, they had these two axes on there to find the optimal point. And I didn't look close enough on there. I know the x-axis was torque. And I was assuming, well, maybe the y-axis is weight or something like that. Turns out it's a $sign.
Oh.
So that means what they were trying to optimize is like, literally bang for the buck.
Right.
Is, how much is the torque that we need here going to cost us? Because we don't want to spend any more for it. So if they're already thinking about that, they're thinking that these motors is, as advanced as they are, because it seems like there's a lot in there, we need to be able to manufacture them for a reasonable price.
Yeah.
$1,000 a piece is not a reasonable price because you've got 40 total actuators. That's $40,000 in actuators. So it can't be $1,000.
Right.
$100 would be great because then we're talking, the actuators are only going to sum up to $4,000. That's pretty reasonable. So the number is somewhere in between there. So I don't know if it's that or if they're talking about the housing, because there's a lot of things they can clean up on the housing to get rid of a lot of those sharp edges that are in there. And there is one actuator in general that has been a big mystery for me. And I'm not sure if we're going to, if I go back and see if we can get a close-up anywhere on here, because we don't see a big close-up. Maybe we do see a little bit here on the wrist. So on the wrist, there's an actuator right down here, just after the elbow. And that is the smallest rotary actuator. So they have 6 actuators, and they tried to come up through a commonality study, the best selection of actuators that they would want to have, because they didn't want to have 14 unique actuators. They wanted to minimize that. Up here in the shoulder, you have 3 of the identical actuators up there. So you're talking about, well, that's pretty good. The best part is no part. Right. So you're not coming up with additional motors. The same 3 motors are used for all 3 axes. In fact, that the same motor is down here in the pelvis area, in 3 places. So it's used 9 times in there. So that motor is like, wow, that's optimal. I mean, it's really used a lot. And then you have these really big gargantuan ones, which I never quite understood either, but you've got 3 of those there that seem to do something else. And then you have one smaller one. And the smaller one is only in the wrist just to do that. That's it. It doesn't appear anywhere else in the body. And it was like, but when you look at it, the mounting mechanism for it is weird. There's like all kinds of holes and slots and everything else in there that seem to have no purpose. Because when it mates to the other, it's connected. Wait a minute, are you missing some nuts and bolts here? What's going on? Is it? I don't think it's necessarily a point that they're going to attach the harnessing to or anything else. It's a real mystery, and it really pokes out, and it just looks odd. So it must be that they had another purpose in mind for that at first. And so my guess is, because it's a very weak motor, and I'm surprised that, it's strong enough for what you need for the wrist. This motor up here in the shoulder, personally, I think that thing's overpowered. That's too big. The first 2, they definitely need that power. This one can be a little bit smaller, but maybe this one was just too wimpy. So they had to size it up. But I wouldn't be surprised if this one could actually go up here well. And now they may have made some decisions that say, well, you know what, this one's a little bit underpowered. Or it's okay if we give it a little bit more, let's bring it up here and do something different. But what my thoughts are is the original Optimus also had 40 actuators in there, but it only had a 6-degree freedom arm. It didn't have 7 because, again, they didn't have the yawing going on there. So do you remember where those other 2 actuators were? Because it's still 40, and they added one here and added one there, which means the count should be 42. But the count is 40 because they removed 2 actuators from somewhere. And do you know where they removed them? Right up here in the head.
The neck, yeah. You said the neck, yeah.
Yep. So when Optimus was initially walking, the very first prototype, evidently sometimes it fell over just when it moved its head
Ah,
So its balance was so bad that just moving the head, it's like, oh no. So, I mean, you got to be pretty clumsy that if just turning your head makes you fall down. So it was like Elon says, wait a minute, we've got cameras all over the place. Why do we need motors in the head? And it was like, yeah, okay, take them out. So it may have been that little teeny motor was
yeah.
also meant to go up the neck area.
Yeah.
And then suddenly it gets scratched. It's like, nah, it's not going to be in there. And that's probably the reason why it's got all these other things in there that just do not make sense to me. And so I think they're going to be doing some cleanup on that design, maybe lighter and tighter. He has said before,
Yeah.
you know, he mentioned that. So maybe they found a way to make it a little bit lighter and tighter
Right.
to get the kind of pop, or maybe they've discovered that some of them are just too big and they don't need that amount of force or that
Right.
amount of torque.
So Scott, I know that there's two parts to this question. One is that the question may be so speculative, it's hard to answer the question, because we really haven't ever had a product that was video in, action out before. So for you to speculate on how quickly now they can train it might be hard, but just in general, what you've seen in this video, knowing that it's now video in, action out, how do you think that that will mean? I mean, they kind of imply it in the video that this is going to make it really super easy to train it. What do you think?
Okay. I mean, that's a big question on how the training is. So there's sort of this initial training set that goes through Dojo. And John Gibb and I had kind of an active discussion about this the other day, is that you're kind of teaching Optimus tactically how to do certain things. And then there may be some tasks that are just sort of in its set of activities that it knows how to do that are very simple. But the question is, how do you teach it a new task? So what we're wondering is like, okay, it knows how to maybe tell colors. It knows how to pick up a part. It and maybe different size parts. It knows how to move them somewhere else. So those are the things it kind of knows how to do. But that's not the actual task here. So they had some interface, and they haven't said this, but we suspect there's going to be something like a large language model where you tell it what you want it to do. You just say, Optimus, put the blue blocks into the blue tray. And then it just does it from there. So that is probably how you will train it through natural language interface. The other possibility is that Optimus will watch what someone is doing and say, and copy, or, you know, literally ape what they're doing. The question is, does it sort of figure out what it is you want it to do? So if I picking up the blue blocks and putting them over there and the green over here, does it understand I'm sorting by color, or it just knows, oh, those always go over to the left and the others always go over to the right, and they just happen to have the same color? You know, does it make that inference on there by itself just by watching a video? So a lot of the video teaching is going to just be the more tactical things of how you do a particular very simple thing, how you pick up a tool, maybe how you pick up a nut and put it onto something. Those are very simple. And then you're going to have the higher level things where you have to say, this is how it's actually done.
Right. All right. So any other thoughts that you had? And again, I just want to apologize to everybody out there that we've had these technical difficulties with my internet today, but I believe that all of this is coming across well, even if Scott's voice is coming and his head hasn't moved for the last 5 minutes, but it's okay. I think it's all coming out. I hope it is. So Scott, any additional thoughts with regard to what you've seen?
I think it's moving along really rapidly. And to me, why did they just decide to release this yesterday? It's not around a big event. Usually we see these around sort of a more important event or something that's kind of coming up. Part of it has been, okay, there's been a dearth of information and everyone keeps saying, oh, we would love to have an Optimus update, but there was no real reason to put it out. And maybe it's because they really hit some milestone and they just want to celebrate. They just want to show it. So the other videos were kind of rushed because they had to be done for Investor Day. They had to be done for Shareholder Day.
Right.
There was no reason to put it out yesterday. They could have put it out next week or the week after. And they decided now is a good time. We believe AI Day from a lot of reports will probably be first quarter of next year.
Right.
So we're not really going to be, so it's not like, oh, it's coming around November. You don't have to show anything. It's like, oh, it's about time. The other is, remember, it was a recruiting video as well.
It was,
the very end was like, join our team.
Right.
We're opening up and we want that. And so they might be saying, we've got to that phase right now that we do need to ramp up. Just like, you can do so much with FSD, but until FSD is mature, there's no reason to have all the beta testers.
Right.
And then you get it to a certain phase, and it's like, yeah, now we need a lot of people.
Right.
And maybe now they need a lot of other people to come join the team to help to do the training and the testing and everything else. Yeah. So that's another possibility. So
that was my main thought. Actually, that was my first thought, was that, you want the best of the best out there if this thing is getting ready to actually go into some kind of production phase. They're talking about, November, which is only 45 days. Well, 45 days till we're in November. So, yeah, it's such an interesting next step here. Whoops. It's entirely possible that we've completely now lost Scott, since all I see is myself. I don't even know if I'm still recording, but in any case, I'm going to pretend like we've just ended the program. And I'll thank Scott in absentia. Thank you, Scott, for coming on and helping us with all of that. And for all of you out there, I want to remind you that there will be the regular Monday morning program, and this will be at probably about 6:30 California time is when that will come out and be published. I'm going to try to get this up by 5 o'clock California time. We'll see if I can accomplish that. All right, that's all I got for you. And again, thanks, Scott, wherever you are. And for all of you out there, it has been great talking to you.